inside every proton, hidden far below the reach of ordinary experience, operates a force so intense that it accounts for nearly all the mass of the visible universe. And yet, despite its overwhelming influence, no experiment has ever witnessed its messenger existing on its own. The gluon is real. It is essential. It cannot be avoided. And still, it never appears in isolation. This is not a failure of our detectors, nor a gap in experimental ingenuity. It is a rule written directly into the fabric of nature itself. Our story begins at the smallest scales we can meaningfully explore, where quarks are bound together by interactions governed by quantum chromodynamics, or QCD. This theory describes the strong force, the interaction responsible for holding the cores of atoms together. Gluons are the carriers of this force, mediating the binding of quarks inside protons and neutrons. But unlike the messengers of light or gravity, gluons refuse solitude. They act everywhere inside matter, shaping its structure and mass, while leaving no solitary trace behind. What appears invisible is doing most of the work. In this journey, we will follow the evidence carefully, step by step, into the very architecture of matter itself, where mass, force, and confinement cannot be separated. We begin with a fundamental and deeply unsettling question. Why can we never see a gluon alone, even though it undeniably exists? The most troubling aspect of gluons is not how difficult they are to detect, but the fact that the laws of physics themselves seem to forbid their isolation. Every particle detector ever constructed, every accelerator ever activated, and every high-energy collision ever analyzed has delivered the same verdict. Quarks appear only in bound combinations, and gluons reveal themselves only through their effects, never as independent objects. This pattern does not arise from technological shortcomings. It reflects how nature is organized at its most fundamental level. In theory, gluons are simple to define. They are the carriers of the strong force, the interaction that binds quarks together inside protons and neutrons. Without this force, atomic nuclei would disintegrate. Stars could not sustain nuclear fusion. The matter that makes up planets, bodies, and galaxies would not remain stable. Quantum chromodynamics describes this interaction with extraordinary precision. Within its mathematical framework, gluons are as indispensable as electrons or photons. And yet, their behavior is profoundly different. Photons travel freely through space, crossing cosmic distances unimpeded. Electrons can be isolated, trapped, and counted one by one. Gluons cannot, no matter how extreme the conditions. No experiment has ever produced a free gluon. The first hints of this strange behavior emerged in the late 1960s at the Stanford Linear Accelerator Center. There, physicists fired high-energy electron beams into protons in a series of experiments known as deep inelastic scattering. The results shattered the idea of protons as smooth, indivisible objects. Instead, electrons scattered as though they were colliding with point-like constituents inside the proton. Richard Feynman famously named these constituents partons. At first glance, the data suggested that quarks might behave almost like free particles when probed at extremely short distances, but every attempt to extract them told a very different story. When researchers tried to pull quarks apart, they never emerged on their own. Instead, entirely new particles formed. The act of separation did not liberate fundamental building blocks. It created additional bound states, as though the energy used to pull quarks apart reorganized itself into new matter. The same pattern appeared when physicists searched directly for gluons. In 1979, experiments at the Petra electron-positron collider in Germany produced a decisive result. Certain collisions generated not two jets of particles, but three. Two of these jets matched the expected behavior of a quark and an antiquark flying apart. The third carried energy and momentum that could only be explained by the emission of a gluon. This was the first clear experimental evidence that gluons existed. And yet, even in this landmark discovery, the gluon never appeared as an isolated entity. It manifested only indirectly, through a cascade of hadrons produced as the strong force reshaped the energy of the collision. The gluon left a distinct signature in the data, then vanished into confinement. It was seen, but never caught. The reason for this behavior becomes clearer when the strong force is compared to electromagnetism. Electric charges interact by exchanging photons, and that interaction weakens as distance increases. The electromagnetic field spreads out, allowing charged particles to separate. The strong force behaves in exactly the opposite way. As quarks are pulled apart, the interaction between them grows stronger. Instead of diminishing, the energy stored in the gluon field increases roughly in proportion to the distance between them. Both experimental evidence and lattice QCD calculations support this picture. Rather than spreading through space, the gluon field tightens into a narrow region, often described as a flux tube. Pulling harder does not weaken the connection. It concentrates energy. Large-scale numerical simulations, first developed in the 1970 seconds and refined using modern supercomputers, reveal what happens next. As separation continues, the energy stored in the gluon field becomes great enough to create a new quark-antiquark pair from the vacuum itself. The original system does not break apart. It divides into two new bound systems. Isolation never occurs. This phenomenon is known as confinement, and it applies not only to quarks, but to gluons themselves. The ultimate reason lies in one defining feature of quantum chromodynamics. Gluons carry the very charge they transmit. In electromagnetism, photons are electrically neutral and do not interact directly with one another. In QCD, gluons carry color charge, which means they interact with other gluons. The strong force is not a simple exchange between particles. It is a self-reinforcing network of interactions, tightening its grip as one attempts to pull it apart. And in that inescapable grip lies one of the deepest truths of the universe. The force that builds matter also ensures that its messengers can never stand alone. That self-interaction, hinted at in the way gluons refuse isolation, transforms the strong force into something fundamentally different from the forces we meet in everyday life. Quantum chromodynamics is not an abelian theory like electromagnetism. It is a non-abelian gauge theory. And within that structure, the force carriers do not merely transmit interactions. They participate in them. Gluons bind to other gluons. Their fields curve back on themselves, and energy concentrates instead of dispersing. The gluon field does not thin out smoothly across space. It organizes, tightens, and locks itself into confined configurations. From the perspective of the theory, this changes everything. A free gluon is not simply hard to produce. It is not a stable physical state at all. And over the decades, experiments have repeatedly converged on that same conclusion. Throughout the 1970 seconds and 1980 seconds, physicists searched extensively for any sign that color charge might escape confinement. They examined cosmic rays arriving from deep space, analyzed lunar soil brought back by Apollo missions, and combed through the debris of the most energetic accelerator collisions available at the time. If quarks or gluons could exist independently, even briefly, the universe should have left behind telltale traces: particles with fractional electric charge, anomalous ionization tracks, or interactions that did not fit the established patterns. None were found. The absence was striking in its consistency. Across environments, techniques, and energies, nature gave the same answer. Today, confinement is treated as an experimental fact. We see its consequences constantly. What remains unresolved is not whether confinement happens, but how to prove it rigorously from the fundamental equations themselves. That gap is so profound that the Clay Mathematics Institute has offered a $1 million prize for a complete proof of confinement and the existence of a mass gap in Yang-Mills theory. It is a rare situation in physics, a phenomenon observed everywhere, understood intuitively and numerically, yet still awaiting a formal mathematical seal. Extreme conditions offer a glimpse of how close confinement can come to loosening its grip. In heavy ion collisions, at facilities like the relativistic heavy ion collider and the Large Hadron Collider, atomic nuclei are smashed together at energies high enough to briefly create a quark-gluon plasma. In this exotic state, quarks and gluons move more freely over short distances. Resembling the conditions that prevailed microseconds after the Big Bang, detectors record collective flows and correlations that signal partial deconfinement, a fluid-like state of matter unlike anything seen under normal circumstances. And yet, the freedom never lasts. As the plasma expands and cools, confinement reasserts itself. Gluons do not drift away as independent particles. They reorganize, binding once more into hadrons. The universe remembers its rules even under the most violent stress. This same physics reaches far beyond particle accelerators and into the structure of the everyday world. Measurements of proton structure reveal a counterintuitive truth. Most of a proton's mass does not come from the intrinsic masses of its quarks. Instead, it arises from the energy stored in the gluon fields and from the restless motion of quarks confined within them. More than 90% of the mass of ordinary matter traces back to this confined dynamics. Gluons, which can never be isolated, determine the weight of the visible universe. As David Gross once summarized, the remarkable feature of QCD is that quarks behave as if they are free at short distances, yet are permanently confined at large distances. That statement is not philosophical rhetoric. It is a compact description of decades of experimental data. The question, then, is no longer whether gluons exist. Their influence is everywhere. The deeper question is why nature is structured so that the carriers of the strongest force can never appear alone. One possible answer lies in stability. If color charge could propagate freely across large distances, the structure of matter would be radically different, perhaps unrecognizable. Another lies in symmetry. The SU3 structure at the heart of QCD forces gluons to interact with one another. Once that self-interaction is present, confinement emerges naturally in every realistic calculation. What remains most striking is the universality of the outcome. Across energy scales, experimental methods, and cosmic environments, the same pattern holds. Gluons reveal themselves only through structure, never through isolation. This constraint has far-reaching consequences. If a gluon cannot exist on its own, then it cannot be understood as an isolated object in the usual sense. Its reality is relational. It appears only through interaction, embedded within a larger framework rather than standing apart from it. And that brings us, seamlessly, to the next puzzle. Part 2. Why would galaxies fly apart if we only count the matter we can see, if we add up every star we can photograph, every cloud we can map, every luminous knot of gas we can measure? The arithmetic tells us that many spiral galaxies should not survive their own rotation. They should shed their outer stars the way a rapidly spinning wheel sheds mud. Yet the night sky is full of elegant spiral disks that have held together for billions of years, rotating steadily, refusing to come apart. The discomfort here is stark and mechanical. Gravity from the visible matter is not enough, and the mismatch is not subtle. To see why this became a crisis, imagine a galaxy in which almost all the mass sits where the light is brightest. In that case, the inner region would dominate the gravitational pull. Farther out, stars would feel less inward attraction, and their orbital speeds would fall with distance. This is exactly what happens in the solar system, where planets move more slowly the farther they are from the sun. That expectation is not aesthetic preference. It follows directly from how gravity behaves when mass is concentrated toward the center. But when astronomers began to measure real galaxies carefully, the outer regions refused to behave. Instead of slowing down, stars far from the galactic center often orbited at nearly the same speed as stars much closer in. This unexpected behavior is captured in what astronomers call a flat rotation curve, a graph that stays high instead of dropping away. If you allow only the gravity of luminous matter, the outer disk should be fragile and unstable. If you trust the observed speeds, then the galaxy must be embedded in a much larger reservoir of mass that does not emit light. This realization did not arrive as a single dramatic moment. It emerged from long nights at telescopes, meticulous calibration, and the gradual elimination of alternative explanations. In the late 1960 seconds and 1970 seconds, Vera Rubin and Kent Ford used sensitive spectrographs to measure how fast different parts of galaxies were moving. By reading tiny Doppler shifts in the light, they could tell whether material was approaching us or receding. Their work on Andromeda and other spiral galaxies helped make the problem unavoidable. By the late 1970 seconds, Rubin, Ford, and their collaborators published extended rotation curves showing that the inferred mass continued to rise with radius, long after the visible light had thinned out. Pause on that implication. In the outer disk of a spiral galaxy, starlight fades, gas becomes patchy, and the visible inventory declines. Yet the orbital speed does not collapse the way it should if the mass were truly disappearing. The simplest interpretation is that the mass is still there, but it does not participate in the electromagnetic world the way ordinary matter does. NASA summarizes this conflict plainly, noting that stars near the edges of galaxies move too fast to be held together by luminous matter alone. Optical observations were not the only doorway into the problem. Radio astronomy opened another. Neutral hydrogen emits radiation at a wavelength of 21 centimeters, a signal that can be tracked far beyond the bright stellar disk. By measuring the Doppler shift of this emission, astronomers could map rotation at much larger radii than optical light allowed. And the flat behavior persisted. The consistency was unsettling. Different instruments, different wavelengths, different teams. The same conclusion. It was not a quirk of one telescope or one method. It was a property of galaxies themselves. Now the logic becomes unavoidable. A star in a circular orbit is not choosing its speed. It is balancing its tendency to move straight ahead against the inward pull of gravity. If that inward pull is too weak, the orbit cannot be stable at the observed speed. In spiral galaxies, we can measure the speed directly from spectroscopy. The stars are telling us, through their motion, that there is more gravity than we can see. We can estimate the visible mass of a galaxy with considerable care. Starlight tells us how many stars are present and what kinds they are. Gas maps reveal clouds of hydrogen and molecular material that do not shine brightly but still contribute weight. With these inputs, astronomers can calculate how much inward gravitational pull the luminous components should provide. And in many galaxies, that pull simply is not enough. Either gravity behaves differently on these scales, or there is additional mass that does not emit light. What makes this conclusion hard to escape is that the discrepancy is not subtle. Rotation curves do not show a marginal mismatch that could be erased by tweaking assumptions. The difference is large, too systematic, and persistent across many kinds of galaxies. Some spirals are bright and massive, others are faint and diffuse. Some are rich in gas, others dominated by old stellar populations. Yet the same pattern appears again and again. When astronomers tried to model this behavior, they were not led to a small correction. They were forced to introduce an extended halo, a roughly spherical distribution of unseen mass surrounding the luminous disk, providing additional gravitational pull at large radii. This is the point where dark matter stops sounding like an optional fix and begins to look like structural necessity. A spiral disk is not a rigid object. It is a dynamically delicate system. Stars move in orderly rotation, but the disk is vulnerable to instabilities, heating, and tidal disturbances. If all the mass were confined to the luminous disk, many galaxies would be far more fragile than they appear. A massive halo changes the rules. It deepens the gravitational potential well, stabilizes the disk, and alters how it responds to perturbations. When astronomers talk about galaxy stability, they are being literal. They are asking whether a rotating system can persist over billions of years without tearing itself apart. It helps to remember what visible matter actually means. Most of what we directly observe in a galaxy comes from stars and gas traced through emission or absorption. Stellar masses are estimated from brightness and color using population models calibrated against nearby stars. Gas masses are inferred from radio lines, such as the 21-centimeter emission of neutral hydrogen and molecular traces like carbon monoxide. These methods are not perfect, but they are anchored to physical measurements, spectra, and cross-checks between independent surveys. Their uncertainties are real, yet bounded. The missing mass problem survives within those bounds. This is why the issue sharpened, rather than faded as astronomy advanced. Early on, it was reasonable to suspect that ordinary matter had been underestimated, perhaps hidden in dim stars, cold gas, or compact objects. But as infrared observations revealed cooler components, as radio telescopes mapped hydrogen more completely, and as stellar population models tightened, the gap remained. The outer orbital speeds were still too high. The visible inventory still fell short. At that stage, a fair question emerges. If this unseen mass truly exists, does it behave consistently across the universe? Or is it simply a label for ignorance? Here the evidence broadens. Dark matter is not inferred from rotation curves alone. It appears in galaxy clusters through the motions of galaxies and through gravitational lensing, where massive structures bend the light of background objects. It appears in the cosmic microwave background, imprinted in the pattern of temperature fluctuations that encode the physics of the early universe. Rotation curves remain especially persuasive because they are local and mechanical. They involve objects moving today under gravity, in a regime where Newtonian reasoning usually works well. The conclusion, delivered calmly but relentlessly by the data, is that a spiral galaxy is not a bright disk floating in emptiness. It is a luminous tracer embedded in something much larger. When you look at an image of a spiral galaxy, most of its mass is not in the part your eyes are drawn to. The stars outline the structure, but they do not dominate it. NASA's summaries are deliberately blunt. Something unseen is tugging on galaxies and holding them together. This local evidence fits into a broader cosmic picture. The European Space Agency's Planck mission measured the cosmic microwave background with exquisite precision and inferred a universe in which ordinary matter makes up only a small fraction of the total. Dark matter accounts for about 26.8% of the universe's mass-energy budget. That number matters. It shows that the missing mass in galaxies is not an isolated bookkeeping error. It is part of a consistent inventory derived from the earliest observable moments of cosmic history. None of this forces a single interpretation. There are alternatives that modify gravity instead of introducing unseen matter. And those alternatives are taken seriously precisely because they make testable predictions. The point is not dogma. The point is pressure. Rotation curves created a crisis that demanded a structural explanation, not a cosmetic one. Galaxies rotate as if extra mass is present. The structural response is to place them inside massive halos that dominate their gravitational fields at large radii. There is also a practical reason rotation curves became so influential. They provide a clean link between measurement and inference. You measure velocity as a function of radius. That velocity profile tells you how the enclosed gravitational influence grows. If the influence keeps increasing with radius while the light fades, something is contributing. Whether that something is unseen mass or a change in gravity, the galaxy itself is telling you that visible matter is not the full story. History matters here. Scientific crises are not resolved by a single elegant graph. They resolve when independent teams, using different tools, repeatedly find the same mismatch. Rubin's optical measurements formed one pillar. Radio maps of hydrogen formed another. Later, large surveys expanded the sample from dozens of galaxies to thousands. The pattern did not dissolve with better statistics. It became more detailed, more classified, and harder to dismiss. If you want a sharp way to hold on to the core idea, keep it mechanical. In the outer parts of many spiral galaxies, stars orbit too fast for the visible mass to bind them. If luminous matter were all that existed, the disk would loosen and disperse. It does not. Therefore, either there is an additional gravitational source in the form of unseen mass, or our understanding of gravity must change in that regime. Observation comes first. Theory must answer to it. And now the next implication follows naturally. If galaxies require an unseen component to remain intact, then that component must also shape cosmic history, influencing how structures formed, how early galaxies assembled, and how the cosmic web grew from tiny fluctuations into today's vast filaments and clusters. Once a rotation curve refuses to fall, darkness stops being a philosophical absence. It becomes an engineering requirement for the universe to build stable spirals at all. That same unseen mass does more than hold galaxies together. It bends the light of distant objects behind them in ways visible matter alone cannot reproduce. And that leads us forward. Part 3. How does the strongest force in nature become invisible at longer distances? The most unsettling feature of the strong force is not how powerful it is, but how completely it vanishes when we try to observe it from afar. At the scale of quarks, it is the strongest interaction ever measured. At the scale of atoms, molecules, or everyday matter, it leaves no direct trace. A force capable of binding the core of matter itself fades so thoroughly that beyond a certain distance it seems not to exist. Most forces weaken as distance increases. Gravity diminishes as masses separate. Electromagnetism spreads out and thins with distance in the same way. The strong force behaves in the opposite manner. When quarks are close together, their interaction is surprisingly mild. As they are pulled apart, the force does not weaken. It grows stronger. This reversal is not a metaphor. It is a quantitative, measured property of quantum chromodynamics. The first experimental hints of this strange behavior emerged in the late 1960 seconds and early 1970 seconds, when physicists began probing protons at ever smaller distances using high-energy scattering experiments. Electrons fired into protons did not behave as though they were striking a smooth, indivisible object. Instead, they scattered as if they were colliding with nearly free, point-like constituents. This unexpected result led to one of the most important ideas in modern physics, asymptotic freedom. In 1973, David Gross, Frank Wilczek, and David Politzer independently showed that the equations of quantum chromodynamics predict a remarkable effect. At extremely short distances, or equivalently at very high energies, the strong force becomes weaker. Quarks, normally inseparable, begin to behave almost as if they are free particles. For this insight, they would later receive the Nobel Prize in Physics. But hidden inside this elegant result was a deeply unsettling implication. If the strong force weakens as distances shrink, then it must strengthen as distances grow. The mathematics of QCD left no alternative. This behavior is not a matter of interpretation. It is a direct consequence of how color charge operates within a non-abelian gauge theory. Unlike electromagnetism, where photons carry no electric charge and do not interact with one another, the strong force is fundamentally different. Gluons carry color charge themselves. They interact not only with quarks, but also with other gluons. The force feeds back on itself. This self-interaction radically alters how the field spreads through space. Instead of dispersing outward, the gluon field pulls itself inward, The field lines attract, bundle, and compress, forming a narrow, elongated structure known as a flux tube. When two quarks are very close together, this tube is short and stores relatively little energy. But as the quarks are pulled apart, the tube stretches, and unlike a stretched rubber band that eventually snaps, the energy stored in the flux tube continues to increase, roughly in direct proportion to the separation distance. There is no weakening. There is no clean break. This picture is not merely qualitative. It has been tested and refined through decades of lattice QCD calculations. By discretizing spacetime into a fine grid and solving the equations numerically, physicists can simulate how the gluon field behaves under controlled conditions. Independent groups, using different algorithms and supercomputers, have reached the same conclusion again and again. The energy does not spread out. It concentrates. Eventually, stretching the flux tube becomes energetically prohibitive. At that point, the field finds a new solution. Rather than allowing the original quarks to separate further, the energy stored in the tube materializes into a new quark-antiquark pair pulled from the vacuum itself. The system does not yield isolated particles. It reorganizes into two new bound states. What began as an attempt to tear matter apart ends with the creation of more matter. This mechanism explains why the strong force becomes effectively invisible at larger distances. It does not fade away. It conceals itself. Beyond the size of a proton, the force is locked inside stable composite particles. Outside those particles, there is no free field left to measure directly. The invisibility of the strong force is not an absence. It is the signature of confinement doing its job perfectly. Historical experiments reinforced this understanding. Throughout the 1,970 seconds, physicists searched for deviations from expected force laws at nuclear scales. If the strong force leaked outward even slightly, it would have produced measurable effects beyond the size of atomic nuclei. None were observed. Nuclear forces appeared short-ranged, saturated, and consistent with confinement. Later, collider experiments provided further confirmation. When quarks or gluons are produced in high-energy collisions, detectors never record isolated tracks. Instead, they see jets, tight sprays of hadrons emerging from the collision point. The angular distributions, energy flows, and internal structures of these jets align precisely with predictions from QCD that assume confinement. The force does not release particles. It reshapes them. One of the most dramatic confirmations came from heavy ion collisions. By smashing together large nuclei at extreme energies, physicists recreated conditions similar to those that existed microseconds after the Big Bang. In this environment, quarks and gluons form a hot, dense medium known as quark-gluon plasma. Over very short distances, color charges move more freely, and the strong force behaves differently. Yet even here, as the plasma expands and cools, confinement reasserts itself. Quarks and gluons do not escape. They lock back into hadrons. These experiments revealed another striking detail. The quark-gluon plasma behaves not like a weakly interacting gas, but like a nearly perfect fluid. This reflects the collective, self-interacting nature of gluons. Even when partially deconfined, the strong force refuses to resemble a familiar long-range interaction. It remains dominated by internal dynamics. The consequences of this invisibility are profound. Confinement explains why atomic nuclei are stable and localized. It explains why matter has definite size and structure, rather than dissolving into a diffuse sea of interacting charges. It explains why chemistry and biology are possible at all, free from the overwhelming influence of nuclear forces. From an experimental standpoint, this behavior posed a deep challenge. Early physicists expected forces to reveal themselves through long-range effects. The strong force defied that expectation. Its presence had to be inferred indirectly, through scattering patterns, mass distributions, and energy flows. Perhaps the clearest demonstration lies in the mass of the proton. The proton weighs far more than the combined masses of its constituent quarks. That extra mass comes from the energy stored in the gluon field and the relentless motion of confined quarks. Through Einstein's E equals mc2, that energy becomes mass, the strong force, invisible outside the proton, dominates its internal energy budget and therefore the mass of ordinary matter itself. This is also why every attempt to detect a free gluon has failed. The force that binds gluons grows stronger with distance. Any attempt to separate them triggers the very mechanism that prevents separation. The harder you pull, the more confinement pushes back. As David Gross once explained to a general audience, the strong force is strong precisely because it does not behave like other forces. It traps its own charges. This trapping is not an added rule or an empirical patch. It is woven into the mathematical structure of the theory. At the heart of this behavior lies the running of the coupling constant. At high energies and short distances, the coupling decreases. At low energies and large distances, it increases. This running has been measured experimentally and calculated theoretically with extraordinary precision. It is one of the most thoroughly tested predictions of the Standard Model. What remains remarkable is how cleanly nature separates scales. Below the size of a proton, the strong force governs quark dynamics. Above that scale, its effects are frozen into composite particles. There is no gradual leakage, no lingering influence. The transition is sharp and complete. And it is this separation that allows other forces, electromagnetism, gravity, and the weak interaction to dominate the larger structures of the universe. From atoms to stars to galaxies, electromagnetism governs the architecture of atoms. Gravity rules the motion of planets, stars, and galaxies. And the strong force, despite being the most powerful interaction ever measured, remains confined to its own narrow domain. It shapes matter at the smallest scales, then withdraws, leaving no direct imprint on the larger structures of the universe. This separation of responsibilities is not accidental. It is the outcome of deep physical principles discovered only through decades of persistence. For many years, confinement was a suspicion rather than a settled fact. Physicists searched relentlessly for cracks in the idea. They looked for free quarks in cosmic rays, for fractional charges in lunar samples, for anomalies in accelerator debris. They refined detectors, pushed energies higher, and revisited assumptions. Each new experiment closed another escape route. Each new calculation reinforced the same conclusion. Nature does not allow color charge to roam freely. Today, confinement is no longer treated as a frustrating limitation. It is understood as an organizing principle. It explains why the strongest force in nature does not tear matter apart. It explains how the universe can be both extraordinarily stable and richly structured. It explains how something so powerful can remain effectively invisible. The strong force does not fade at long distances. It completes its task and withdraws. Its invisibility is the signature of its success, and that realization leads naturally to a deeper question. If the strongest interaction in nature becomes hidden beyond the scale of quarks, then its influence must reappear indirectly, shaping mass, stability, and the internal dynamics of everything we observe. To understand how that happens, we must confront one of the most disruptive facts in particle physics. Part 4. Why do gluons interact with each other? Not just with quarks. The most unsettling feature of gluons is not simply that they bind quarks together. It is that they refuse to restrict their interactions to quarks alone. Unlike other force carriers that act as neutral messengers, gluons respond directly to one another. This single property transforms the strong force from a simple exchange into a dense, self-reinforcing network that reshapes matter from the inside out. In quantum chromodynamics, gluons are defined as carriers of color charge. That definition immediately sets them apart from photons. Photons transmit electromagnetic force, yet they carry no electric charge themselves. Two photons can cross paths without noticing one another. Gluons cannot. Each gluon carries color charge, and color charge interacts with color charge. As a result, every gluon is both a messenger and an active participant in the force it conveys. This feature was not added by hand. It emerges inevitably from the mathematical structure of the theory. QCD is built on a non-abelian gauge symmetry, specifically the SU3 symmetry associated with color. In such a framework, the force carriers must inherit the charge of the interaction. Once that symmetry is fixed, gluon self-interaction is unavoidable. When the theory was first developed in the early 1970s, the consequences were not immediately obvious. Many physicists initially expected the strong force to resemble electromagnetism, with additional complexity layered on top. That expectation collapsed under closer inspection. When the equations were examined carefully, new interaction terms appeared, terms that described gluons coupling directly to other gluons. The force was no longer linear. It folded back on itself. David Gross later reflected on how surprising this realization was. The equations themselves were compact and elegant, but their implications were radical. Once self-interaction entered the picture, intuition borrowed from electromagnetism stopped working. The strong force obeyed a different logic entirely. This self-interaction explains why the strong force behaves unlike any other. When quarks exchange gluons, those gluons are simultaneously interacting with one another. The field does not spread smoothly through space. It knots, twists, and reinforces itself. Energy does not dilute with distance. It concentrates. Lattice QCD calculations provide a direct window into this behavior. By solving the equations of QCD numerically on discretized spacetime grids, physicists can watch how gluon fields evolve. These simulations, refined over decades using vast international supercomputing efforts, supported by institutions such as NASA and ESA, show that gluon fields form dense, interconnected structures even in the absence of quarks. The field never switches off. It interacts with itself continuously. This overturned earlier assumptions. It became clear that the strong force is not mediated by isolated exchanges, but by a collective field whose components cannot be cleanly separated. Each gluon influences the behavior of all the others. Confinement emerges not as an imposed rule, but as a natural consequence of this networked interaction. Experimental evidence aligns precisely with this picture. In high-energy collisions, gluons reveal themselves through jet patterns that differ measurably from those produced by quarks alone. The angular distributions, energy flows, and internal substructure of these jets match predictions that explicitly include gluon-gluon interactions. Without self-interaction, the observed data cannot be reproduced. One of the clearest examples comes from three jet events in electron-positron collisions. Two jets correspond to a quark and an antiquark. The third jet signals gluon emission. But the story does not end there. The internal structure of that third jet carries the unmistakable imprint of gluon self-coupling. The way energy fragments and redistributes inside the jet only makes sense if gluons interact with one another before confinement locks them into hadrons. Heavy ion collisions deepen this understanding even further. When large nuclei collide at extreme energies, they briefly produce a medium dominated by gluons. In this quark-gluon plasma, gluon self-interaction governs the collective behavior of the system. Experiments show that the plasma behaves not like a weakly interacting gas, but like a strongly coupled fluid. This behavior is a direct consequence of gluon-gluon interactions acting at high density. Theoretical work had predicted this long before it was observed. Calculations showed that at sufficient energy density, gluon self-interaction would dominate the dynamics of the plasma. When experiments at RHIC and the Large Hadron Collider confirmed these predictions, confidence in the non-abelian nature of QCD solidified. This network-like behavior has a final, profound consequence. because gluons interact with each other. The strong force does not act independently at each point in space. Local changes ripple through the entire field. Pulling on one part of the system rearranges the whole network. This is why attempts to isolate quarks or gluons fail so completely. Separation does not weaken the force. It activates its collective response. The acceptance of this idea was gradual and hard-won. But once understood, it revealed the strong force not as a simple binding agent, but as a self-organizing system, one that hides its power precisely by using it perfectly. Early resistance to this picture came largely from habit. For decades, physicists had grown comfortable with forces carried by neutral messengers, photons, for electromagnetism, hypothetical gravitons for gravity. A force whose carriers interacted strongly with one another felt unruly, even inelegant. Yet the data refused to cooperate with intuition. Every serious attempt to describe the strong interaction without gluon self-interaction failed. By the late 1970 seconds and into the 1980 seconds, the convergence was unmistakable. Jet studies in particle colliders, scaling violations observed in deep inelastic scattering, and increasingly sophisticated lattice QCD simulations all pointed to the same conclusion. Gluons must interact with gluons. Remove that feature, and quantum chromodynamics collapses as a viable theory. This single property does more than explain confinement. It also explains why the strong force is responsible for most of the mass of ordinary matter. Inside a proton, gluons are not passive intermediaries. They are in constant conversation not only with quarks, but with one another. Energy is exchanged, redistributed, and compressed into a tiny region of space. That energy density dominates the proton's mass budget. In this sense, mass is not primarily a property of constituent particles. It is a property of an interacting field. Gluon self-interaction ensures that energy remains confined, dense, and persistent. Without it, protons would be far lighter, nuclei far less stable, and matter, as we know it, would look profoundly different. The same mechanism underpins nuclear stability. The strong force binds quarks into nucleons, and residual effects bind nucleons into nuclei. Gluon self-interaction keeps this binding localized and robust. It prevents the force from leaking outward and disrupting larger structures. From a broader perspective, this balance is what allows the universe to support complexity at all. A force that binds too weakly cannot form stable matter. A force that spreads too freely would overwhelm structure. Through gluon self-interaction, the strong force confines its influence to the smallest scales while shaping everything built upon them. Carl Sagan once remarked that understanding nature often requires abandoning familiar analogies. Nature is subtle and elegant, he said, but not malicious. In the case of gluons, the subtlety lies in accepting that force carriers need not behave like messengers at all. They can be participants in a collective system. That collective behavior is now central to modern physics. It guides how simulations are constructed, how experiments are interpreted, and how new states of matter are predicted. It also sets strict constraints. Any future theory that aims to extend or replace QCD must reproduce gluon self-interaction with extraordinary accuracy. What remains striking is how much structure flows from this single feature. By carrying color charge, gluons transform the strong force into a self-coupled network. That network confines quarks, generates mass, and stabilizes matter. It does so quietly, without revealing itself directly, leaving behind only the particles we can observe. If gluons interact so intensely with one another that they dominate the internal energy of matter, then that hidden interaction must account for most of the mass we measure in the visible universe, even though the constituent particles themselves contribute very little. Part 5. Could gluons be the real reason why protons are heavy? The most unsettling fact about the proton is that nearly all of its weight comes from something that has no weight of its own. Add up the masses of the 3 quarks inside a proton, and you recover only a small fraction of the proton's total mass. The rest does not come from undiscovered particles or exotic ingredients. It comes from energy specifically, from the energy stored in gluon fields that never escape the proton. For much of the 20th century, mass was treated like a ledger. Add the masses of the constituents, and the sum gives you the mass of the whole. That intuition works well for atoms, molecules, and even nuclei. It fails completely for protons. A proton has a mass of about 938 mega-electron volts. The combined masses of its up and down quarks contribute only a few % of that value. Something else is doing almost all the work. Quantum chromodynamics provides the answer. Inside the proton, quarks are confined by gluon fields that interact violently with one another. These interactions trap enormous amounts of energy in a tiny volume. According to Einstein's relation between mass and energy, that energy contributes directly to mass. The proton's mass is therefore determined not by what its quarks are, but by what they are doing and by how strongly they are bound. This realization did not arrive overnight. In the 1,960 seconds, deep inelastic scattering experiments showed that quarks behave almost like free particles when probed at extremely short distances. That discovery raised an obvious puzzle. If quarks are nearly massless and weakly interacting at short scales, where does the proton's mass come from? As theoretical understanding matured in the 1,970 seconds, the answer sharpened. The strong force weakens at short distances but grows dramatically at larger ones. Inside the proton, quarks are confined by gluon fields that do not spread outward. Those fields store energy continuously. The tighter the confinement, the higher the energy density. Lattice QCD calculations delivered the first quantitative confirmation. By simulating quarks and gluons on discretized space-time grids, physicists were able to compute the proton's mass from first principles. The results were remarkable. Even when quark masses were set close to their measured values, the simulations reproduced the full proton mass. The missing mass came from gluon energy and the motion of confined quarks. This was not a numerical coincidence. Independent lattice groups, using different algorithms and computing platforms, reached the same conclusion. The proton's mass is an emergent property of interacting fields, not a simple sum of parts. Experiments reinforced this picture. Measurements of proton structure functions revealed that gluons carry a substantial fraction of the proton's momentum. Despite having no rest mass in high-energy collisions, gluons dominate the proton's internal dynamics. The proton behaves less like a bag of particles and more like a dense knot of interacting energy. One of the clearest demonstrations comes from studies of momentum sharing. As collision energy increases, gluons become more numerous. They split, recombine, and interact incessantly. At sufficiently high energies, gluons carry most of the proton's momentum, a result measured repeatedly at accelerators and predicted precisely by QCD. Behind this understanding lies a profound shift in intuition. Early models pictured quarks as small, massive objects glued together by a force. QCD replaced that image with something far less familiar. Quarks move relativistically. Gluons form a self-interacting field. Mass arises from dynamics, not substance. The Higgs mechanism plays only a supporting role here. It gives quarks their small intrinsic masses, but those masses account for only a few % of the proton's total. The rest, the overwhelming majority, comes from the restless, invisible, self-interacting gluon field that binds matter together. Turning off gluon interactions would strip away most of the proton's weight, even if the Higgs field stayed exactly as it is. That distinction matters, because it separates two ideas that are often blurred together in popular discussions. The Higgs mechanism explains why fundamental particles like quarks and electrons have intrinsic mass at all, but the mass of everyday matter, the mass that makes planets heavy, muscles tired, and mountains immovable, mostly comes from something else: confined QCD energy. We have indirect confirmation of this difference from how protons behave under extreme conditions. In heavy ion collisions, when a quark-gluon plasma forms, confinement weakens for a brief moment. The familiar hadrons lose their rigid borders. Quarks and gluons move more freely, never as clean, isolated objects, but as components of a hot, dense medium. Then the system cools. Confinement returns, and mass reappears in the form of hadrons once again. It is as if the universe briefly melts the rules of ordinary matter, then refreezes them, converting energy stored in fields back into the masses of particles. The pattern of this transition is exactly what QCD predicts. Astrophysical evidence points in the same direction. The mass of stars, planets, and living organisms is dominated by protons and neutrons. If gluon energy did not contribute so heavily to hadron mass, the universe would be dramatically lighter. Stellar evolution would shift. Gravitational collapse would follow different thresholds. Cosmic structure would assemble in unfamiliar ways. The fact that it does not because the cosmos behaves as it does quietly reflects the central role of gluon dynamics in setting the weight of the visible world. From a theoretical standpoint, this picture resolved a puzzle that once seemed almost embarrassing. It explained why protons are heavy even though their constituents are light. It also clarified why that mass is stable. Gluon interactions are confined. Their energy cannot simply leak away into space. Because confinement does not allow a slow bleed out of color charge. As long as confinement holds, the energy stays trapped and therefore the mass stays put. That same confinement explains something else that feels mundane only because we are used to it under ordinary conditions. Protons do not decay. The energy that gives them mass is locked inside. There is no easy channel for it to escape without breaking the rules of QCD. Stability is not an extra feature patched onto the theory. It follows naturally. What makes this story especially compelling is how little it asks us to add. No new particles are required. No hidden mechanisms need to be invoked. The same gluons that bind quarks are also the ones that generate most of the mass. One interaction accounts for two fundamental properties of matter, structure and weight. And the pattern is not unique to protons, neutrons, mesons, and other hadrons follow the same logic. Their masses reflect the energy of interacting gluon fields. The differences between them arise mostly from how quarks are arranged and how the fields organize, not from large differences in the intrinsic masses of quarks themselves. This perspective also forces a subtle redefinition of what weight really means. Mass is not simply a count of how much stuff is present in hadrons. It is largely a measure of how much energy is confined. And that energy is enormous relative to the system's size. The proton's radius is about 0 femtometers, yet it contains nearly a giga-electron-volt of energy. The density implied by that fact is extreme, nor is that density a static lump. Gluon fields fluctuate, concentrate, and redistribute energy continuously. Those fluctuations feed directly into measurable proton properties, its spin, the way momentum is shared among constituents, and even its internal pressure profile. Recent experiments that map internal forces in the proton have revealed pressures that exceed those found in neutron stars, generated entirely by confined QCD dynamics. Not because protons are exotic objects, but because confinement compresses energy into a volume so small that ordinary language breaks down. The way these insights were established matters too, because it highlights how physics actually advances. No single experiment delivered the answer in one dramatic stroke. The conclusion emerged from decades of scattering data, theoretical refinement, and computational leaps. Each line of evidence structure functions. Jet physics, lattice calculations approached the proton from a different direction, and all arrived at the same destination. Most mass is field energy, and gluons are its primary architects. Today, the claim that most of the mass of ordinary matter comes from gluon energy is no longer controversial. It appears in textbooks. It is reproduced by precision lattice computations. It is consistent with the way protons behave in experiments. And still, it remains deeply counterintuitive because we live in a world where solidity feels fundamental, when in reality, solidity is an emergent consequence of confinement, motion, and interaction. This understanding also constrains the future. Any extension of the standard model that hopes to be taken seriously must reproduce the proton's mass with the same accuracy. It must preserve how gluon self-interaction generates confined energy, and how that energy appears as mass. There is little room for creative interpretation here. The proton is not merely one more particle in a zoo, it is a calibration point for the universe. There is also a practical edge to all of this. Technologies that rely on nuclear physics, from energy generation to medical imaging, depend on the stability and mass of hadrons. That stability is not accidental. It is a direct consequence of gluon dynamics, of confinement, of the fact that the strong force completes its work internally and refuses to leak outward. Seen this way, the proton is not heavy because it contains heavy things. It is heavy because it is busy. Its interior is a constant exchange of energy among quarks and gluons, confined so tightly that energy becomes mass. And if mass emerges primarily from gluon interaction rather than from substance, then the gluon itself cannot be treated as an ordinary particle in the everyday sense. Its presence is not something you can bottle or isolate. It appears as a temporary excitation within quantum fields, real, measurable in consequences, but never granted an independent existence outside interaction. Which brings us naturally to the next question, because if confinement is what makes matter stable, then the only way to truly see what gluons and quarks are, rather than what they produce, is to force matter beyond the regime where confinement holds. Part 6. What happens when gluons and quarks are liberated in extreme conditions? The most unsettling realization in modern nuclear physics is that protons and neutrons can lose their identity completely when matter is heated or compressed. Far enough. Under ordinary conditions, they feel solid, indivisible, final. But QCD predicts a limit push temperature or density beyond a critical threshold, and the familiar boundaries of matter fail. Confinement weakens. The force that normally traps quarks and gluons reorganizes itself. Matter enters a new phase, quark-gluon plasma. This is not speculative philosophy. It is a direct consequence of QCD, supported by theory, numerical simulation, and experiment. Lattice QCD calculations indicate that at temperatures of roughly 2 trillion Kelvin, the energy density becomes high enough to disrupt the confined structure of hadrons. Quarks and gluons are no longer locked into individual protons and neutrons. They move within a shared medium. And the first place this state existed was not in a laboratory. It was the early universe. Cosmological models indicate that during the first few microseconds after the Big Bang, the universe was too hot for protons or neutrons to exist. Matter was a dense, rapidly expanding plasma of quarks, gluons, electrons, and photons. Only as the universe expanded and cooled did confinement emerge. Quarks became locked into hadrons. The familiar building blocks of matter formed only after that transition. For decades, this phase of cosmic history was effectively sealed away. No telescope can see that far back. Even modern instruments observe the universe long after this transition. The quark-gluon plasma era left no direct light behind for us to photograph. To learn about it, we had to recreate it briefly, violently, and on purpose. That effort accelerated in the late 20th century. Physicists built machines capable of colliding heavy nuclei at extreme energies, compressing and heating matter to extraordinary conditions. By smashing nuclei together at nearly the speed of light, they could momentarily produce energy densities similar to those of the early universe. Facilities such as the relativistic heavy ion collider and later the Large Hadron Collider were designed to push this frontier. When gold or lead nuclei collide head-on, hundreds or thousands of particles erupt outward. But the most important signals are not individual particles. They are collective patterns, subtle flows, correlations, suppressions that reveal the properties of the medium formed in the collision. Early expectations were almost naive in hindsight. If quarks and gluons were freed, many assumed the plasma would behave like a weakly interacting gas particles liberated, flying independently, disorderly and thin. The data contradicted that picture immediately. Measurements showed that the plasma behaves like a nearly perfect fluid, with extremely low viscosity, a medium that flows collectively, coherently, as though gluon self-interaction still dominates even in partial liberation. And that is the twist that makes the quark-gluon plasma so haunting. Even when confinement weakens, the strong force does not become simple. It becomes collective. It becomes a different kind of order, one where quarks and gluons are not isolated objects, but components of a shared, strongly coupled substance. The hadrons dissolve, not into freedom, but into a deeper form of togetherness. Instead of dispersing into free, weakly interacting particles, the system displays strong collective motion. This outcome caught many physicists off guard. Even when quarks and gluons are no longer locked inside individual hadrons, they continue to interact intensely with one another. Confinement weakens, but gluon self-interaction does not disappear. The strong force remains dominant, reshaping itself rather than fading away. The plasma flows, responds to pressure gradients, and redistributes energy with remarkable efficiency. What changes is not the existence of the strong force, but the way it manifests. One of the clearest experimental signatures of this behavior is known as jet quenching. In high-energy collisions, energetic quarks or gluons normally fragment into narrow, well-defined jets of particles. But when such jets pass through quark-gluon plasma, they lose energy rapidly. The surrounding medium absorbs and redistributes that energy. Detectors record jets that are distorted, broadened, or in some cases almost erased. This dramatic energy loss reveals just how dense and interactive the plasma is. A weakly interacting gas could not produce such an effect. Another key observation comes from collective flow patterns. Particles emerging from heavy ion collisions exhibit correlated motion that reflects pressure gradients present in the earliest moments of the plasma's existence. These flow patterns align strikingly well with hydrodynamic models that treat the plasma as a strongly coupled fluid. The agreement between theory and experiment is not marginal. It is precise, persistent, and difficult to dismiss. Behind these conclusions lies a careful chain of inference. Physicists do not observe quark-gluon plasma directly. They reconstruct its properties from thousands of correlated measurements: particle yields, momentum distributions, angular correlations, and energy flow. Each observable provides a fragment of information. Together, they form a coherent picture. Lattice QCD offers an independent line of support. By calculating the thermodynamic behavior of strongly interacting matter, physicists can predict the temperature range at which confinement breaks down. These predictions match the conditions inferred from experiments. The transition is not abrupt like ice melting into water, but it is well defined and reproducible. The story of quark-gluon plasma is also a story of technological progress. Early accelerators lacked the energy and precision required to explore this regime. Advances in detector technology, computing power, and data analysis made it possible to extract subtle signals from overwhelmingly complex events. International collaborations refined their techniques over decades, steadily improving confidence in the results. What emerges from all this evidence is a view of matter under extreme conditions that challenges everyday intuition. Liberation does not mean simplicity. Even when quarks and gluons are no longer confined into hadrons, they do not behave as isolated entities. The strong force remains active, shaping the medium as a whole. This behavior has profound implications for cosmology. During the quark-gluon plasma era of the early universe, matter behaved collectively. As the universe expanded and cooled, confinement emerged smoothly rather than abruptly. Quarks locked into hadrons, Gluons became confined. Energy stored in the plasma reorganized itself into the masses of particles. This transition set the stage for everything that followed. Without it, protons and neutrons would not exist. Without protons and neutrons, nuclei could not form. Without nuclei, atoms, stars, planets, and life itself would be impossible. The large-scale structure of the universe depends sensitively on how quark-gluon plasma cooled and confined. Astrophysical environments may still host matter under related conditions. The cores of neutron stars reach densities far beyond those found in atomic nuclei. Some theoretical models suggest that quark matter or exotic QCD phases may exist deep within their interiors. Observations of neutron star mergers and gravitational waves provide indirect clues. Though many details remain uncertain, what is clear is that quantum chromodynamics governs matter across an extraordinary range of conditions, from the interior of protons to the earliest moments after the Big Bang. The same underlying rules apply. Quark-gluon plasma is not an exotic anomaly. It is a natural phase of matter under extreme conditions. This realization reshaped nuclear physics. The field expanded beyond the study of static particles to encompass phases of matter. Concepts from fluid dynamics, thermodynamics, and statistical physics became central. The strong force revealed itself not only as a binding mechanism, but as a driver of collective behavior. Carl Sagan often emphasized that understanding the universe requires following evidence wherever it leads, even when it contradicts expectation. The quark-gluon plasma did exactly that. It showed that liberation does not erase interaction. It transforms it. The experiments that revealed this state did not provide a single dramatic moment of discovery. Instead, they built a case slowly, measurement by measurement. Each result added weight. Each refinement sharpened the picture. Today, quark-gluon plasma stands as one of the most robust findings in high-energy nuclear physics. From a broader perspective, it teaches a precise lesson. Matter is not defined solely by its particles, but by how those particles interact under given conditions. Change the conditions enough, and matter reorganizes itself completely. The strong force permits this transformation because it is flexible. It confines at low energy. It collectivizes at high energy. It governs both stability and change using the same underlying rules. In a liberated state, quarks and gluons no longer behave as discrete objects at all. What emerges instead is a collective pattern, where fields and fleeting excitations carry physical reality, and interaction, not individuality, defines what can be observed. Part 7. Is a gluon a particle, or merely an excitation of a field? The most unsettling feature of a gluon is that it cannot be pointed to as a thing in the usual sense, even though its effects dominate the structure of matter. Every experiment that reveals a gluon does so indirectly, through patterns of energy, momentum, and correlation. Nothing ever appears that can be cleanly separated, stored, or observed at rest. This forces a deeper examination of what physicists actually mean when they use the word particle. In modern physics, a particle is no longer imagined as a tiny, solid object. Quantum field theory replaces that picture with fields that exist everywhere, all the time. What we call a particle is a localized excitation of one of those fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. In this framework, gluons are excitations of the color field described by quantum chromodynamics. This distinction matters because the color field behaves unlike any other known field. It does not allow its excitations to exist independently. A photon can propagate freely through space because the electromagnetic field is linear and its excitations do not strongly interact with one another. The color field is non-linear. Its excitations interact continuously with each other. That interaction reshapes what it even means for a gluon to exist. The foundations of this view were laid in the mid-20th century, when quantum field theory was extended to describe forces through symmetry principles. The strong interaction required a symmetry more complex than electromagnetism. That symmetry, SU3, organizes how color charge behaves. Once this symmetry is imposed, gluons emerge naturally as the quanta of the color field. What follows from that symmetry is unavoidable, because the underlying symmetry is non-abelian. The field cannot remain passive. It necessarily interacts with itself. The equations that define quantum chromodynamics contain terms in which one gluon directly influences another. These terms are not decorative additions or adjustable features. They are mathematically unavoidable. Remove them, and the theory loses its internal consistency and predictive power. As a consequence, a gluon cannot be treated as a simple ripple traveling through an otherwise quiet background. From the very moment physicists attempted to describe what a free gluon would look like, the problem became apparent. In quantum field theory, a particle can be defined cleanly only when the field it belongs to becomes weakly interacting at large distances. That condition allows an excitation to separate from the rest of the system and propagate independently. For gluons, this condition is never satisfied. As distance increases, the interaction strength does not fade. It grows. The color field never enters a regime where a single excitation can detach and persist on its own. This is why the question, is a gluon a particle, does not admit the same answer it does for electrons or photons. A gluon is unquestionably real, but its reality is inseparable from interaction. It exists only as part of an evolving collective system rather than as an isolated entity. Experimental evidence reinforces this interpretation at every scale. When particle accelerators generate energies high enough to produce gluon activity, detectors never register a solitary gluon track. Instead, they observe jets of hadrons whose internal structure encodes the presence of gluon excitations. The gluon announces itself through correlations, angular patterns, and energy distributions, not through direct capture. The classic three-jet events in electron-positron collisions illustrate this clearly. One jet aligns with a quark, another with an antiquark, and the third carries the unmistakable signature of a gluon. Yet even here, the gluon does not appear as a single object. It materializes as a cascade, a reorganization of the color field into many bound particles. The gluon shows up as a pattern, not a standalone particle. Lattice QCD sharpens this picture further. By solving the equations of the strong interaction numerically on discretized spacetime grids, physicists can examine gluon behavior without relying on small interaction approximations. These calculations reveal gluon excitations that are highly delocalized and strongly coupled. They behave nothing like independent particles. Instead, they resemble fluctuations within a tightly bound, constantly interacting field. This framework naturally explains why gluons contribute so powerfully to mass and internal pressure inside hadrons. Energy stored in interacting fields contributes to mass. And because gluons interact relentlessly with one another, they dominate the energy density inside protons and neutrons. The proton's mass reflects the dynamics of the field, not the presence of heavy constituents. The conceptual shift from particles as objects to particles as excitations has deep historical roots. Early quantum physicists wrestled with the wave-particle duality of light and matter. Over time, quantum field theory provided a language that dissolved this tension. In that language, waves and particles are complementary descriptions of the same underlying structure. For gluons, the wave and field description is not optional. It is essential. The particle picture, while convenient in calculations, is often misleading when taken literally. This realization resolves multiple puzzles at once. It explains why free gluons are never observed. It clarifies why confinement emerges naturally rather than being imposed by hand. It reveals why gluon self-interaction dominates the strong force. All of these features follow inevitably once gluons are treated as field excitations, embedded in a non-linear, self-interacting system. The behavior of quark-gluon plasma reinforces this conclusion. Even in this extreme state, where confinement weakens and quarks and gluons move over short distances, gluons do not behave like free particles. The medium exhibits collective motion. Energy and momentum flow through the field as a whole. Individual excitations are fleeting, short-lived, and inseparable from the environment around them. This collective behavior surprised many physicists who initially expected a gas of liberated particles. Instead, experiments revealed a strongly coupled fluid. That outcome aligns naturally with a field-centric view of reality, where interaction, not individuality, defines physical behavior. Theoretical work anticipated this long before experimental confirmation. Calculations showed that even at high temperature and density, the color field would remain strongly correlated. Excitations would not decouple. The plasma would act as a unified system rather than a collection of independent particles. When experiments at RHIC and the LHC confirmed these predictions, confidence in the field-based interpretation deepened. This distinction also clarifies why gluons resist localization. To localize an excitation, one must isolate it from its surroundings. For gluons, isolation strengthens interaction. The harder one tries to separate a gluon, the more violently the field responds. The very attempt to pin it down destroys the conditions required for a particle-like description. This is not a limitation of detectors or experimental ingenuity. It is a structural feature of the theory itself. Quantum chromodynamics does not permit gluons to exist as asymptotic free states. The mathematics forbids it. Carl Sagan often reminded audiences that scientific progress depends on refining the language we use to describe nature. Familiar words, he warned, can mislead when applied beyond their proper domain. The word particle is one such case. For gluons, it is a useful shorthand, not a literal description. Understanding gluons as excitations of a self-interacting field aligns naturally with how modern physics treats all fundamental interactions. Fields are primary. Particles are emergent. This perspective unifies phenomena across scales, from the interior of a proton to the earliest moments of the universe. It also sets firm boundaries. Any future theory that seeks to extend or replace quantum chromodynamics must reproduce this field-dominated behavior with extraordinary precision. The gluon cannot be simplified into a free messenger without breaking the structure of matter itself. Any framework that claims to extend or replace quantum chromodynamics must first pass a very high bar. It must recover this defining behavior in full. It must explain why gluon excitations can never exist as isolated entities, and why. At the same time, their influence can be measured with astonishing precision in experiments. This requirement is not philosophical. It is practical. Every realistic simulation of nuclear matter, every reliable prediction for collider experiments, and every credible interpretation of high-energy astrophysical data depends on treating gluons not as independent particles, but as manifestations of a deeply self-interacting field. Any model that treats gluons as ordinary messengers quickly produces results that contradict observation. What emerges instead is a coherent and internally consistent picture. A gluon is not a tiny object darting back and forth between quarks. It is a localized excitation of a field whose defining feature is that it never disengages from itself. Its existence is inseparable from the environment in which it appears. Attempting to extract it destroys the very conditions that allow it to be defined. This does not weaken the reality of gluons. It clarifies it. Gluons are real because their effects are real, repeatable, and quantitatively precise. Their reality is written into interaction, not isolation. Once gluons are understood as transient excitations of a self-interacting field, attention naturally shifts away from trying to capture them directly and toward understanding how the field reorganizes itself as matter forms, fragments, and recombines. These reorganizations leave clear experimental fingerprints, even though the excitations themselves never appear alone. Patterns in jets, energy flow, and particle correlations become the true observables. Part 8. Why doesn't the glue that binds quarks ever let them go? The most unsettling feature of the strong interaction is not merely that it binds quarks together, but that every attempt to pull them apart produces more matter instead of freedom. No matter how much energy is applied, no matter how violent the collision, quarks never emerge alone. The force that binds them does not weaken, does not snap, and does not release. It answers tension by transforming it. In everyday experience, bonds break when stretched far enough. Materials thin, fracture, and fail. Our intuition is shaped by forces that weaken with distance. The strong force violates this intuition completely. Quantum chromodynamics predicts, and experiments confirm, that the energy stored between separating quarks increases steadily as the distance between them grows. There is no regime in which the interaction fades. The farther the quarks are pulled apart, the more energy accumulates in the gluon field connecting them. This behavior was far from obvious when quarks were first proposed. Early models imagined them bound by forces similar to electromagnetism, only stronger. That picture quickly collapsed under experimental pressure. If the strong force behaved like electromagnetism, sufficiently energetic collisions should have produced free quarks. Decades of experiments showed that they never did. The breakthrough came when physicists realized that the strong force does not spread itself thin through space. Instead, the gluon field contracts. As quarks separate, the field tightens into a narrow region rather than dispersing. Energy becomes localized instead of diluted. Lattice QCD calculations made this concrete. When quarks are placed on a discretized space-time grid and gradually separated, the total energy of the system rises almost linearly with distance. This result has been reproduced by independent groups for decades. It does not depend on numerical tricks or adjustable assumptions. It is a direct consequence of the theory. As separation continues, the system reaches a critical point. The energy stored in the gluon field becomes large enough to create a new quark-antiquark pair from the vacuum. No external matter is required. This follows directly from quantum field theory, where concentrated energy can convert into particle-antiparticle pairs. When this happens, the original quarks do not escape. The system reorganizes. Each original quark pairs with one of the newly created partners. One stretched connection becomes two bound systems. The number of particles increases, but none are freed. This process, known as hadronization, is not an exceptional outcome. It is the default response of the strong force to separation. Every high-energy collision observed in particle detectors reflects this rule. Energetic quarks and gluons never appear as isolated tracks. They fragment into jets of hadrons, the visible consequence of field energy repeatedly transforming into matter. The experimental record is extensive. In electron-positron collisions, quark-antiquark pairs are produced with enormous energies. Detectors never observe the quarks themselves. Instead, they register sprays of hadrons aligned with the original directions of motion. The detailed distribution of particles inside these jets matches QCD models of hadronization with remarkable accuracy. The same behavior appears in proton collisions, and in heavy ion collisions, regardless of environment or energy scale. Confinement reasserts itself once energy is redistributed, even in quark-gluon plasma, where confinement is temporarily weakened. The pattern returns as soon as the system cools. Quarks and gluons reorganize into hadrons. The strong force does not forget its rules. At the heart of this behavior lies a decisive difference between the strong force and other interactions. In electromagnetism, force carriers do not interact with one another. Field lines spread outward and weaken with distance. In QCD, gluons interact directly with other gluons. This self-interaction prevents the field from dispersing. Energy remains localized. Pulling on one part of the system triggers a response across the entire field. Separation provokes reorganization. The historical search for free quarks illustrates how rigidly this rule is enforced. Throughout the 1970 seconds and 1980 seconds, physicists examined cosmic rays, lunar samples, and accelerator debris, searching for particles with fractional electric charge. If quarks could ever exist freely, even briefly, traces should have appeared. None did. Experiments improved sensitivity again and again. Limits tightened. The absence remained absolute. Theoretical work mirrored this conclusion. Models that attempted to soften confinement or allow partial freedom consistently failed to reproduce observed data. Only theories in which energy grows with separation matched reality. Confinement emerged not as a hypothesis but as a non-negotiable feature of QCD. The implications reach beyond particle physics. Confinement explains why nuclear forces are short-ranged. Although the strong force is immensely powerful, it does not leak beyond hadrons, outside protons and neutrons. Its influence is sealed. This containment allows atoms to exist without being torn apart by nuclear interactions. Chemistry, biology, and stable matter depend on this boundary. This boundary is not arbitrary. It arises because energy in the gluon field converts into matter before it can propagate outward. The force completes its work internally and leaves behind stable, color-neutral structures. This also explains why attempts to measure the strong force directly at long distances fail. There is nothing to measure. The force does not act between separated objects. It acts only within confined systems. The story of confinement is therefore not one of hidden particles, but of forbidden outcomes. Nature does not merely hide quarks and gluons behind experimental difficulty. It prohibits their isolation through the structure of its laws. Tension is never released. It is transformed. When the equations of QCD are examined carefully, solutions corresponding to isolated color charges are unstable. The system naturally evolves toward configurations where color is neutralized locally. Stability follows from confinement. This is why hadrons always appear in color-neutral combinations. Protons in neutrons, and mesons carry no net color charge. The strong force enforces this condition relentlessly. Any attempt to violate it triggers particle creation on timescales far shorter than any detector can resolve. By the time particles reach our instruments, confinement has already reshaped the event. What we observe are hadrons, not the quarks or gluons that initiated the interaction. As Carl Sagan often noted, nature reveals its rules through consistency. In the case of confinement, that consistency spans energy scales, experimental techniques, and environments. The same outcome appears everywhere. The strong force does not permit partial freedom. It does not allow exceptions. And that's the point that's easy to miss if we focus too much on the fact that gluons never show up as lonely too. Isolated tracks. In high-energy physics, an object earns its reality through necessity. If a single hypothesis is required to make thousands of unrelated measurements line up across decades, across continents, across detector technologies, across energies that differ by orders of magnitude, then that hypothesis is no longer optional. It becomes structural. That is exactly what gluons are in the modern Standard Model, not a thing you can bottle, but a thing you cannot remove. So when we ask, what does the experimental evidence really say about gluons? We are not asking whether anyone has photographed a gluon like a speck of dust on a microscope slide. We are asking whether the universe behaves as though gluons exist. And it does. It behaves that way obsessively, redundantly, and with a kind of merciless consistency. The cleanest arena, historically, was electron-positron annihilation because it strips away the mess of composite projectiles. When an electron and a positron collide, they don't bring internal structure with them. They annihilate into energy. And that energy becomes whatever the interaction rules allow. In the early era of these experiments, the dominant signature was the one QCD all but demanded two narrow, back-to-back jets. a quark and an antiquark, created in the collision, trying to separate and failing so their energy collapses into hadrons along two opposing directions. It was elegant, it was repeatable, and then, as energies climbed, the symmetry broke, not because nature changed its mind, but because the same rules began to express themselves more richly. At higher energies, the quark-antiquark pair could radiate, and in QCD, the thing they radiate is not light, it is color. It is a gluon excitation, another disturbance in the strong field born from the fact that color charge cannot accelerate without paying a price. That price was seen in 1979, in the Petra electron-positron collider in Germany, when detectors began recording events that didn't resolve into two jets at all, but three. This was not a minor statistical wobble. It wasn't an artifact that went away with better calibration. The geometry was too clean, too stubborn. Two jets carried the hallmarks of quark fragmentation. The third carried energy and momentum that had to come from somewhere. And its angular pattern fit precisely what QCD predicted for gluon emission. It is hard to overstate why that moment mattered, because it wasn't merely we saw something that could be interpreted as a gluon. It was that every alternative that tried to avoid gluons failed to reproduce the observed angular correlations. The gluon wasn't visible as an isolated particle, but it was visible as a required term in the bookkeeping of energy and momentum. The collision had made a third direction of violence, and only a gluon could carry it. That is why people sometimes call Petra's three-jet events the first clear experimental confirmation of the gluon. Not a photograph, a signature, a fingerprint left in motion, and then the story deepened. Because not all jets are created equal, once experiments began sorting jets by their internal structure, they discovered a subtle but decisive difference. Jets associated with gluons tended to be broader and more populous, more hadrons, more fragmentation, more spray. Jets associated with quarks were comparatively tighter. This wasn't aesthetic. It followed from a core fact you've already built into the narrative. Above, gluons carry color charge themselves. They can radiate more readily. They can split and multiply through self-interaction. Quarks radiate gluons, but gluons radiate gluons. And so a gluon-initiated jet naturally fans out into a richer cascade. Detectors didn't need to isolate a gluon. They only needed to measure how energy fell apart. And again, the measurements matched QCD with unnerving precision. As accelerators improved, this evidence didn't stay confined to one historical triumph. It spread into a network. Physicists began measuring how the fraction of three jet events changed with energy, how jet shapes evolved as collision energies increased, how momentum was distributed inside jets, how often gluon-like sprays appeared versus quark-like sprays. Each of these tests was aimed at a different facet of the same underlying claim that QCD's force carrier behaves like a self-interacting, color-charged excitation. Each test agreed, and then there was the second major pillar, deep inelastic scattering. When you fire high-energy electrons into protons, you are not merely hitting a ball, you're interrogating the proton's internal momentum budget. The scattering pattern tells you how momentum is partitioned among the constituents that the electron can effectively see. The earliest Proton picture, born from those late 1960 seconds experiments, initially made quarks look almost free at short distances. But the deeper the measurements went, the more the accounting refused to close with quarks alone. A substantial fraction of the proton's momentum behaved as though it belonged to something electrically neutral, something invisible to the electron's charge coupling. Quarks could not carry all the momentum, so something else had to. That something else was precisely what QCD predicts in abundance at high-energy gluons. And the most telling detail was how this momentum share changed with energy. As probing energies increased, the number of gluons inferred inside the proton increased too. The strong field, under high-energy scrutiny, behaves like a living medium, gluons splitting, multiplying, and filling the available phase space. This wasn't hand-waving. It was the observed pattern of scaling violations, the fact that distributions did not remain constant with energy, the way naive free particle models would suggest. Those deviations were predicted. They were measured, and without gluons, they would have been inexplicable. Then, proton-proton collisions pushed the story into its modern form. At the Large Hadron Collider, most of what happens in the heart of the collision is not quark against quark. It is gluon against gluon. This alone is a quietly astonishing fact. The dominant actors in the highest energy collisions humanity has ever created are entities that cannot be isolated in principle. We do not collide particles in the everyday sense. We collide dense, fluctuating regions of field energy inside protons, where gluon excitations are so numerous that they dominate the statistics of what follows. And when the data arrive, jets, energy flow, rare processes, QCD works, not vaguely, not poetically, quantitatively. The evidence becomes even more visceral in heavy ion collisions. Because now we are not just asking whether gluons exist, we are asking what matter becomes when gluon dynamics saturate an entire region of space-time. In these experiments, the key signals are collective. They are not single particle tracks, but patterns that require a medium behavior that makes no sense if the collision debris is just a loose gas of free fragments. Jet quenching is one of the clearest examples. An energetic parton that would normally create a sharp jet passes through the quark-gluon plasma and loses energy violently. The jet emerges distorted, broadened, or partially erased. That lost energy doesn't vanish. It is absorbed and redistributed by the medium, meaning the medium has to be dense, interactive, and strongly coupled. In other words, gluon-dominated. Here, the gluon's presence is not seen as a particle. It is seen as drag, as resistance, as the medium's refusal to let energy pass through unscathed. Quarkonium suppression adds another layer. Bound states of heavy quark-antiquark pairs can dissolve in the plasma, depending on how the color field screens their binding. The pattern of suppression depends sensitively on the properties of the gluon field in that hot, dense environment. And again, the observed hierarchies align with the expectations of QCD. Even outside the dramatic world of colliders, gluons leave fingerprints. The proton's mass is 1. Lattice QCD calculations reproduce the proton's mass from first principles. And they do so in a way that makes the core message unavoidable if you remove gluon dynamics. You remove most of the proton's weight. The agreement between calculated hadron masses and measured hadron masses is not a coincidence. It is the strong force translating field energy into mass exactly as relativity demands. Proton spin is another. Decades of polarized scattering experiments show that quark spins alone cannot account for the proton's total spin. Gluons contribute significantly, and their contribution has been measured through how spin-dependent structure functions evolve with energy. Once again, a story that refuses to work without gluons becomes coherent the moment gluons are allowed to do what QCD says they must. And that diversity is what makes the evidence so hard to escape. It isn't one experiment. It isn't one clever detector. It isn't one historical decade. It is a lattice of mutually reinforcing necessities. Jets demand gluons, scaling violations demand gluons, momentum distributions demand gluons, heavy ion collective behavior demands gluons, hadron masses demand gluons, spin decomposition demands gluons. Remove gluons, and you don't merely lose one explanatory tool. You lose the ability to make sense of the entire experimental record at once. Which brings us back to the unsettling truth at the start of this part. Every proof is indirect. And yet, the indirectness is the strength, because the evidence does not rely on one fragile chain of inference. It rests on thousands of separate chains that all converge on the same conclusion. A gluon is not seen. A gluon is required. And that raises the next question naturally, almost inevitably. Because if gluons are everywhere in the data but nowhere as isolated objects, then we have to ask what the word exist really means in a theory built from fields. Parton, if gluons are real only through patterns, What does that imply about reality at the smallest scales, about what counts as an object? What counts as a cause? And what counts as something that can be said to be there at all? And that broader shift changes the emotional weight of what we've been saying, because once you accept that gluons are real but ungraspable, not hidden by technology but excluded by the structure of the laws, you're forced into a quieter, stranger conclusion. Maybe the most fundamental things aren't things. Maybe they're rules. Maybe they're symmetries. Maybe they're patterns that can never be separated from the system that sustains them. And in that sense, Part 10 is not just an add-on, it is the natural endpoint of everything the evidence has been trying to teach us from the beginning. Experimental physics builds confidence by convergence, multiple independent roads arriving at the same destination. But here, the convergence comes with an eerie companion, negative evidence. Decade after decade, detectors have become sensitive enough to register single electrons, to count photons, to trace tracks with exquisite precision. And yet, in all that sensitivity, across cosmic rays, lunar samples, accelerator debris, and every imaginable environment, nothing has ever behaved like a free color charge. Nothing has ever behaved like a liberated gluon. The silence is not a gap in the record, it is part of the record. And it matches QCD's prediction with unnerving fidelity. In other words, the gluon is confirmed twice. Confirmed by what appears when QCD says it should. Confirmed by what never appears when QCD says it must not. That symmetry between presence and absence is not a philosophical flourish. It is one of the strongest forms of scientific evidence we have. It is the reason the gluon reshaped what physicists mean by confirmation. Not all truths arrive as a bright dot on a screen. Some arrive as constraints so strict that nothing else survives contact with the data. And that's why the gluon is so psychologically unsettling. It is essential to everything we measure inside matter. Yet it refuses to exist in the way our instincts want it to. It will not sit alone. It will not travel as a free object. It will not offer you the satisfying moment of isolation, storage, and display. Instead, it announces itself through structure, through jets, through scaling violations, through momentum budgets inside the proton, through energy loss in dense nuclear matter, through the very mass of the particles that make up the world. Remove gluons from the equations and the experimental record fractures, not gradually, instantly. So what, then, are we really looking at when we say the word gluon? Part 10. Could gluons be nothing more than a deep pattern in nature? The unsettling possibility is not that gluons are imaginary. The unsettling possibility is that they are not objects in the way we instinctively imagine objects to be. They are indispensable, measurable, and unavoidable, yet always inaccessible as standalone entities. That combination forces one final step, shifting our idea of reality away from things and toward organized behavior. Quantum chromodynamics begins with symmetry, not decoration. Not aesthetics, symmetry as an engine. Choose the symmetry group that governs color, charge SU3, and the rest follows with a kind of cold inevitability. Gluons do not enter the theory because someone decided the world needed them. They enter because once you demand local symmetry of color, you must introduce field components that repair the symmetry everywhere in space and time. In that sense, gluons are not ingredients sprinkled into nature. They are consequences. This becomes clearer when we compare QCD to electromagnetism. Electromagnetism comes from a simpler symmetry. Its field is linear in the relevant sense. And its excitations, the photons can propagate freely. Photons do not carry electric charge, so they do not strongly couple to other photons in ordinary conditions. The theory naturally admits clean, isolated particle states. QCD is different at the root. Its symmetry is non-abelian. The field is non-linear. Its excitations carry the very charge they transmit. Gluons are not neutral messengers, they are charged participants. And that single difference changes the meaning of excitation itself. It means that what you are calling a particle is embedded inside a self-interacting network that never truly turns off at long distances. The conditions required for an isolated, free gluon state, the kind of state you could treat like a photon, traveling through empty space, are never met. So the question is, a gluon a particle becomes subtle in a way that is an electron a particle does not. A gluon is a particle, in the pragmatic sense that quantum field theory describes localized excitations, and experiments measure their signatures. But it is not a particle in the naive sense of an independent, separable object with a free existence out there on its own. In QCD, the environment is not optional. The interaction is not a perturbation. The interaction is the stage itself. That is why the idea of pattern stops being metaphor and becomes a precise description. In modern physics, many real entities are not objects, but stable behaviors of underlying systems. A sound wave is real, measurable, and predictable. Yet it is not a thing you can isolate from the air that carries it. An ocean wave is real, yet it cannot exist without water, gravity, and motion. Its reality is distributed across a system. Gluons belong in that category. They are organized behaviors of a quantum field, sustained by symmetry and enforced by self-interaction. Their being is inseparable from the field configuration that supports them. And here is where lattice QCD makes this almost painfully concrete. In large-scale numerical simulations, physicists do not insert little gluon balls by hand. They define the symmetry, define the interaction rules, discretize space-time, and let the equations run. Gluonic behavior emerges automatically. Confinement emerges. E-fluid tubes emerge. Hadronization emerges. The proton's mass emerges. The thermodynamic transition into quark-gluon plasma emerges. The gluon is not painted onto reality. It is what the rules produce. That's why the simulations don't just give qualitative agreement. They produce numbers that match the world hadron masses, jet-related distributions, momentum sharing, thermodynamic properties of QGP. And if you remove gluonic degrees of freedom, if you try to build the strong interaction without them, the agreement collapses. So in one sense, gluons really are bookkeeping devices for symmetry. They encode how color charge must behave if the symmetry is local and consistent. They encode how the field must respond to itself to preserve the theory's structure. They are not arbitrary. They are demanded. But calling them bookkeeping devices risks implying they are merely mathematical fictions. And that's not what the data allow. Because bookkeeping devices do not create three-jet events in 1979. Bookkeeping devices do not dominate proton collision dynamics at the LHC. Bookkeeping devices do not account for more than 90% of the mass of ordinary matter through confined field energy. Something physically active is there, shaping energy flow, shaping mass, shaping the stability of matter, and doing so with repeatable precision. So perhaps the right way to say it is this: gluons are real, in the way a rule can be real. Real not because you can point to one and say there it is, but because the universe behaves as though the rule is inescapable. And because the patterns the rule produces are measurable everywhere we look. And if that's true, then the deeper implication is quietly radical. Matter might be secondary to interaction. Protons are heavy not because they contain heavy constituents, but because they are regions where interaction energy is trapped so tightly that energy becomes mass. The stuff of the world is not just substance, it is structured activity. Fields and symmetries do not merely describe reality. They may be what reality is at the deepest level. And once you see the gluon this way, the final unease lands almost by itself. If the strongest force in nature is carried by entities that cannot exist alone, then perhaps alone is not a category the universe recognizes at all. Perhaps, at the foundation, the universe is not built from things. Perhaps it is built from relationships, from constraints, from patterns that can be measured, tested, and trusted without ever being held in isolation. And that is where part 10 truly ends, not with the disappearance of the gluon, but with the realization that its refusal to appear alone may be the most honest clue we've ever been given about what fundamental really means. Over the last century, physics has been drifting quietly but relentlessly away from substance and towards structure. Space and time are no longer a silent stage set behind events. They bend, they stretch, they answer back to energy and momentum. Fields are no longer invisible scaffolding we use for calculations. They are actors. They push, pull, store energy, and shape what can exist. And particles are no longer tiny, indivisible marbles. In modern theory, they are excitations fleeting, context-dependent ripples whose identity is inseparable from the fields that sustain them. Gluons sit at the heart of that transformation, because without gluons, quarks would not bind. Without binding, protons would not exist. Without protons, atoms would never assemble. Stars would never ignite. Planets would never form, and the visible universe as we know it would simply fail to take shape. And yet the engine behind all of that stability is something we never witness directly. The strongest force in nature does its work in the dark, leaving behind only the finished architecture. Across wildly different scales, the picture remains consistent. High-energy experiments in particle accelerators confirm the predictions of quantum chromodynamics with astonishing precision jet patterns, scaling violations, momentum sharing, hadronization, all of it matching a theory that insists gluons cannot stand alone. Astrophysical realities depend on the same hidden machinery. Stellar structure and nucleosynthesis rely on the masses and stability of hadrons, masses that arise overwhelmingly from gluon dynamics. Even our cosmological models of the early universe depend on that transition from quark-gluon plasma to confined matter, a phase change that set the stage for everything that followed. And when space-based observatories NASA, ESA, and the James Webb Space Telescope look deep into cosmic history, they are peering into epochs long after confinement had already done its decisive work. Yet those observations would be impossible to interpret correctly without knowing how matter acquired mass and stability in the first place. In a very real sense, gluons, though never seen, still shape every photon those telescopes collect, because they shaped the matter that emitted it. The story of how we came to understand this follows a pattern that repeats throughout science. Nature often reveals itself not through direct display, but through constraint. We learn what is allowed by watching what never happens. Free gluons never appear. Fractional charges never appear. Isolated color charge never appears. These absences are not missing pages in our knowledge. They are signals, hard boundaries drawn by deep structure. The universe is telling us something by refusing, consistently, to permit certain outcomes. Carl Sagan often reminded audiences that the cosmos is under no obligation to match our instincts. Explanation comes from following evidence, even when it pulls us away from familiar pictures. The gluon story is that lesson made concrete. Again and again, the evidence points away from things and toward the rules that govern relationships between things. And none of this means gluons are imaginary. On the contrary, their effects are among the most precisely measured in physics. It means their reality is relational. A gluon is defined by what it does, not by where it can be placed. It is less like a particle you could isolate, and more like a rule being enforced locally, relentlessly, everywhere inside matter. Gluons ensure color charge is conserved. They ensure energy remains confined. They ensure the strong interaction behaves consistently across scales, from the interior of a proton to the earliest moments of the universe. This is also why any future theory, any deeper framework that aims to unify forces or explain their origin, must reproduce QCD's behavior with extraordinary fidelity. Even small deviations would ripple outward into observable violations. Confinement would weaken. Mass generation would shift. Stable matter might not exist as we know it. The margin for error is, for all practical purposes, zero. In that sense, gluons are guardians of structure. They maintain the integrity of matter without ever presenting themselves for inspection. Their presence is felt everywhere and seen nowhere. And so, as this series closes, what remains is not a mystery left hanging, but a picture that is coherent and complete. Gluons are real, indispensable, and experimentally unavoidable. They bind quarks, generate most of the mass of ordinary matter, shape nuclear behavior, and govern the earliest phases of the cosmos. Yet they never exist alone, never appear as isolated objects, and never leave direct tracks in detectors. That combination is not a flaw. It is a clue. It suggests that at the deepest level we currently probe, reality is organized not around isolated things, but around patterns of interaction enforced by symmetry. Gluons are among the clearest expressions of that idea. And with that understanding in place, the story of gluons comes gently to rest, not as a puzzle unresolved, but as a lesson learned about how nature chooses to build a universe. If you're listening as this final thought settles, may the steady order beneath the complexity offer you a sense of calm. The same rules that bind quarks into protons also hold the stars together and keep the night sky stable above us. Wherever you are, and however this journey has accompanied you, may the rest that follows be deep and untroubled. Good night.